Hello, everyone. The topic of this lecture is splines. In previous lecture, we talked about the data points. Once the data point is exact data, we are doing the interpolations, and we talk about the Lagrange interpolations, that is pass one function over all the data points. In this slide, we are looking at an important example that shows a limitation of the high-order polynomial interpolation. This function is called classical rank functions, and it was specifically designed by Carl Runge to demonstrate potential problem when we use the higher order global interpolations. We are considering the interval -1 to the 1, and this is the graph over these intervals. Now we consider nine equally spaced points, okay, with the from the over this interval is mean -1 to the ones, and with the spacing of the point 25 that is shown here. And we construct a Lagrange interpolation polynomials, which result in eighth order polynomial functions that pass through over all of these data points. Once we construct these polynomials and compare it with the true functions, as you can see, these polynomial function is mean the Lagrange is passed through all the data points. However, even though it matches the data point perfectly, we observe the strong oscillations, especially at the end of the intervals, okay, um, for this graph. And this behavior can lead to numerical instability when using the higher degree interpolations. This example illustrates an important idea. A polynomial that passes through all the data points does not necessarily provide a good approximation. As we can see, the higher order global interpolation um, it make more oscillations, okay, once we compare with the real function. For this reason, it's not recommended in the practice. So what is the solutions? In practice, we usually prefer another approach, such as the piecewise interpolation method, like as a splines, which help reduce these oscillations that you saw in the previous slide and produce more stable results. Okay. Um, In the previous slide, we saw that the higher order global interpolations can produce oscillation and instability, especially when we try to fit one polynomial or one function that pass through all the data points. One of the practical alternatives to avoid this problem is piecewise interpolations or local interpolation, which is called splines. The simplest type of the spline is a linear spline. A linear spline is connect the data point using the local linear interpolation. This means we draw the straight line, as you can see in the figure. Okay, we draw the straight line between each pair of the neighboring points instead of using one global polynomial over the entire intervals. In this figure, the red dot, okay, is show the exact data points, and that is just as a samples from the functions, and the green line show the linear spline that connecting those points. Notice that this approach follows the data well and avoids the large oscillation that we saw in the previous slide, is meaning once we are using the higher order polynomial function. However, there is an important limitation. The function itself is continuous, as you can see, but its derivative is not continuous at the data points. In some engineering application, this is acceptable because the continuity of the derivative is not a concern. Okay, again, this is the comparison between these two methods, okay, is meaning Lagrange interpolation and linear splines. As we can see, both of these methods is passed through the exact data points, is meaning the green dots. However, their behavior between the points is very different. The red curve is show the Lagrange interpolation and show the strong oscillation, especially mm, nearing the boundary of the interval. But in contrast, the blue curve is show the or represent the linear spline, connect the points smoothly without oscillation. And this is as a piecewise or local interpolations. And This local as a linear and it provides a more stable and reliable approximation. This show an important idea in practice. A local method can actually perform better than the higher order global methods or global interpolations. Look at this example and to understand how the linear splines work in the practice. First, we choose these functions and then select some data points from this function, is mean from the GX. In this example, we pick these 4 points, 5, 7, 8.5, and 10, and we compute the corresponding function value. Next, we plot the function from the 5 to the 10, and we will use these sample points to build the spline approximations. We construct, as you can see, we construct the linear spline interpolation that is between each pair of the data points. We estimate the value by using the straight line that connect the two pairs data point together. So instead of one global polynomials, we connect the data point using the straight line segments. On the plot, we can see three things. The first one is a true function that's shown by black lines. The linear spline as a red lines and the data points. As you can see, the linear spline has exactly through all the data points as we expected. However, between the points, since the approximation as a linear piecewise, it doesn't perfectly capture. See, if you look at it, doesn't perfectly capture the the curvature of the function, and however, it remains stable and doesn't produce the oscillation. And this is about the linear splines. But as you can see, and there is a limitations for the linear splines because the derivative is not continuous at the data points. If if the derivative is important, okay, we cannot use the linear spline. The next idea is to improve smoothness by using the locally quadratic interpolations, which leads to what we call quadratic splines. With quadratic spline, we can enforce continuity of the first derivative at the data points. However, there is still a limitation. The second derivative remains discontinuous at the data points. Because of this, quadratic spline are not as commonly used in the practice. And we can improve it, okay, by using the cubic splines. To improve this, and to ensure that both the first and the second derivative are continuous across the data points, we define a piecewise interpolation by using the cubic polynomials instead of linear or quadratic ones. Cubic splines maintain continuity of the function as well as the first and the second derivatives across the data points. This produces a curve that is smooth and visually natural while still avoiding the oscillation problems of the high order global interpolations. In the next section, we will develop the formulations of cubic splines. Let's look at the simplest possible example of the cubic spline. Suppose we have these three data points, and therefore we have two intervals, and we need to construct two cubic polynomial function over these three data points, S0 and S1. S0 on the interval of the x sub naught to the x sub 1, and S1 is on the interval of the x1 to the x2. And these are the functions, and as you can see, this is the function of the S0, and this is as a S sub 1. As you can see, each cubic polynomial has a four coefficient A, B, C, and D. And together we have the eight unknowns coefficient. So in total, we need eight equations to determine these eight unknowns. How to find these coefficients? First, the spline must pass through to the given data points, and this give us the following conditions. Okay, it means we are evaluate x0, x1, and x2, and these equations, and we have to find the exact value. Okay, that the data is given. The next one, we require the spline to have a continuous for the first and the second derivative at the x1, because the x1 has a common point between these two polynomial functions. And this connection, again, connect these two cubic polynomials and create a smooth curve across the intervals. And this is the three other equations for meet these criteria. Now we have six equations, but we have eight unknowns, okay, or we have eight coefficients, but only have a six equation. So we need the two additional conditions to solve the system. These extra conditions are provided at the beginning and end of the data set and are called boundary condition or end conditions. In this example, they are applied at the x naught and x sub 2. Once we specify this boundary condition, we will have enough equation to determine all the spline coefficients. The type of cubic splines depends on the boundary conditions chosen by the user. Different boundary conditions lead to different spline types. Once the coefficients are nouns, interpolations become straightforward. Okay, for example, for any value of the x, okay, first we find the intervals it belongs to, and then we evaluate the corresponding cubic polynomial function. Mm, and again, as you can see, for each segment, okay, each segment has a own cubic functions, and we can find any value of the x in these intervals. Okay. Now we need to find all the coefficients of the cubic spline for each interval, and we only do this one time. Okay, that means we are solving for the A, B, C, and D coefficients, and then we define other. Then we find the equation. Okay. Look at this table of the data. As you can see, the H is showing here. The H represents the spacing between consecutive X value, and the second parameters, okay, that show by A, okay, A represents the function value at each node. Okay, it's meaning the yi equal ai. So the a coefficient come directly from the given data points. The other coefficient is meaning b, c, and d depends on the cubic spline we are using. Um, and we are using because different cubic splines, okay, has a different boundary conditions. Okay. To fully determine the spline, we need to specify two conditions at the endpoints, okay, because for make it for make it as a determined conditions, okay, we need to define these two conditions at the end points. One's common choice is natural spline, also called the free spline. In this case, we set the second derivative at the both end points equal to the zero. Okay, it's meaning the value of the second derivative at the beginning data point and the end data point equal zero. Another common choice is a clamp spline, where we specify the first derivative at the end points. In other words, we force the slope of the curve at the beginning and the end point is matched to match to the noun's value. These are the two commonly used boundary conditions, but other combinations are also possible. The important point is that we always need two independent conditions to uniquely determine the splines. Once the type of the cubic spline is determined, we can find the remaining coefficients, meaning B, C, and D. You can refer to the appendix to see how these coefficients are calculated. Let's look at one example. In this example, four data points are given. Since we have a 4 points, the number of the interval is three. One, two, three. And it's meaning we have, excuse me. So we have three spline function, S naught, S sub 1 and S sub 2 on for each interval. For example, the S sub naught correspond to the interval from the X naught to the X1 and similarly for the others. From the data tables, the value of the A naught to the A sub 3 are simply the corresponding the Y value at each node. So the coefficient, so this coefficient is main coefficient of A come directly from the given data, and we know that this value. Also, we define the step size is meaning the edge, okay, and the edge is represent again the distance between the consecutive x value. The goal is determine the cubic polynomials for each intervals. For this reason, now we have to find the remaining coefficients. According to the step presented in the appendix, for all the interior points, is mean j from 1 to the n minus 1, the coefficients of C are determined by using the following equation. These equations form a three diagonal system for these coefficients. For this example, we apply these equations at point x1 and x2 because we have four data points. Okay, for this reason, the interior data points is x1 and x2. We still need two additional conditions to complete the systems. Here we choose the free ends or natural spline boundary conditions. According to the definition of the natural splines, we have to set the second derivative at the endpoints equal to the 0. Once we take the second derivative from the functions and equal to the 0, we find the value of the C sub naught and C sub 3 equal to the 0. Now we have enough equation to solve for all the C coefficients. See, this is the matrix, okay, that we find for finding the C coefficients. The first and the last row come from the boundary conditions, okay, as a free end conditions or natural splines. And the middle rows come from applying the spline equations at the interior points. This result is a three diagonal system that we solve to find the coefficient of the C naught to the C sub 3. Once we find the C values, we can easily compute the remaining coefficients, meaning D and G, by using these equations. Okay, let's look at these examples. Okay, this is the exact functions, and this is the four data points that we are picked for these examples. And now we are using the natural splines, okay, and we should determine each of the coefficients, is meaning A, B, C, and D. I 0, 1, 2, 3. Okay. These four data points is given. Okay. Now we know that the y is represent the value of the a. This is a sub naught. The next one is h or interval steps. Okay. The difference between these two steps is 2. Okay. This is 0. The next one is the interval between the 8.5 and 7 is the 1.5, and this is the third steps is 1.5. The condition as a natural spline for these examples. For the natural splines, the C coefficient is fine based on these equations. 1, 0, 0, 0. Okay, because the second derivative at the beginning points should be equal 0. Zero, 0, 0, 1. Okay, this is about the condition for the end points. C0, C1, C2, C3. Okay, as you can see, for finding the C coefficients, okay, the equation are involving with the step size or in intervals or h, okay, and the a, okay. We determine the h and a, okay, at the beginning of these problems. The a is represent the value of the y, and the h is the difference between the two consecutive x. Now we plug it to this matrix 1, 0, 0, 0. H0 plus H1, 2 plus 1.2, 1.5. For H3 is H sub 1 is mean 1.5 and 0. This is 0. Let me rewrite. we have 1 0 0 0. For the third row, we have 0. H1 is meaning 1.5. The value of H sub 1 is 1.5. 2 times H sub 1 plus H sub 2. 1.5 plus 1.5. 0 0 0 1. And this is about the right hand side. A2 minus A1 is meaning these two values. A sub naught 16.48. This is for the second row. Okay, we will do it for the third and the last row. For the last row is 0. For the third row, again, we plug this value, is meaning the H and A in this equation, and just I write the final answer. 42, this is for C sub 2. The value of the C sub 1 is negative 26.577. Let me rewrite this matrix and vector. We have 1 2 0 0. Again, this number is coming from these equations. Once we solve these equations, these four system of linear equations, okay, the value of the C is negative 1.776, 15, approximately at 0. And this is correct, okay, because we know that the value of the C naught and C sub 3 is 0. Okay, we can say this is approximately as a 0. Once we find the C, then we plug two equation of D and B and find the value of these coefficients. The equation for finding the D is just I try to find the D sub naught, okay, and then we can apply for the rest of the D, okay. For example, for D sub naught, we have 1 over 3 times H sub naught, okay, that the value is 2. CK plus 1 is meaning the value of the C C1 plus the value of the C naught. The value of the C naught, we can use the 0 or this value. The value of D sub naught approximately as a negative 0.758. This is the other value for the D. Because for these 4 data points, we have 3 intervals, okay, or we have 3 cubic splines. This is D, this is the value of the C, this is the value of the D. Now we have to find the B. For finding the B, we are applying these equations. For example, for finding the B sub naught, or finding the value of the B for the first cubic spline or for first intervals, we have 1 over H naught, A1 minus A naught, C1. Now we plug this value. The value of the H naught is 2. A1 is represented Y sub 1 is 26.277. A naught or Y sub naught, the value is given as a 16.418. The C naught and C1 we found previously. This is the C1 and C2. Sorry, this is the C naught and C1. To 7.962, and this is the value of the B for another intervals. This is for B sub naught. I have already shown you how we can find it. This is B sub 1. This is B sub 2. Now we find all of these 4 coefficients, okay? And for example, I'm going to write the polynomial functions, okay, or S sub naught for the first intervals based on A sub naught, B sub naught, C and D, C naught and D naught. Okay, this is the cubic functions. And we can use the rest of the coefficient for finding S sub 1 and S sub 2. Because again, we have 4 data points. We need three cubic splines, okay, to connect these four data points together. Okay, this is the solution I show you. I have already shown you. Okay, once all the spline coefficient are known, interpolations is straightforward. And for any value of the x, okay, we first determine which interval it belongs to. Then we simply use the corresponding spline functions. Okay, for example, if the x is belong to the s sub g, okay, we are using these spline functions, and then we evaluate it or find the value of the x sub x bar by using these cubic equations. This is about the coding for finding the locations, okay, or for to understand which interpolations you have to use it, or the x is located to which intervals. This figure shows a comparison between the original function and the natural cubic spline. Cubic spline. As you can see, the splines passes smoothly through all these data points, okay, and um, there is no oscillations, okay, between these between the data points, okay. And since this is as a natural spline, the curvature at the endpoint is set to the 0, which influences how the curve behavior near the boundary. This is the comparison between the original function, cubic spline, and Lagrange interpolation. As you can see, the Lagrange and the natural spline, these two methods pass through to the same data points, but the splines follow the function more smoothly, especially near to the end, near or especially between the points, data points. But for the Lagrange interpolation, that is as a global functions, okay, and global interpolations, okay, we have some oscillations, okay, and as we can see, or we can say, we have a large deviations, okay, between the functions and these global interpolations. For this reason, the splines provides better behaviors, okay, relative to the Lagrange, because this is as a local or piecewise function. Another type of the boundary condition is called clamp end condition. If we know the slopes at the end points, we can use those value instead of the natural spline condition. In this case, we directly specify the first derivatives of the spline at the beginning and the end point of the data points. So we set the derivative at the x naught equal 0 and equal to the value that is defined by users, okay, and the derivative at the x sub 3 is equal to the known slope at the last point. Since the derivative at the nodes corresponding to the b coefficients, this gives us the b naught and b sub 3, and this value equals to the slopes, okay? And this method is force the spline to match the desired slopes at the boundary. Once we are using the natural clamp spline, the the determinant of the C coefficients, okay, for the clamp spline, we need to revise it, okay? As you can see, the first and the last row that is represent the boundary conditions, okay, is changed, but the other columns is meaning the entire data points, okay, entire of this matrix, okay, um, internal data is similar to the natural splines. And now we find the value of the coefficient of the C. Once the C value are known, then we can compute the remaining spline coefficient, is meaning D and B, by using these two formula. For endpoints, the last clamp boundary equation is written as shown. This replaces the last equation in the matrix system and includes the known slope at the end points. If we solve the previous examples based on the clamp splines, okay, we have to we have to modify this matrix based on the clamp conditions, okay. Once we solve it, we find the value of the C, then we can find the D and B based on by using these two equations. Now we compare the clamp splines with the original function. As you can see, this spline also passes through all the data points, like as the Lagrange and the natural splines. Okay, since we specify the slope at the endpoints, the curve also match the desired behavior near the boundaries. As a result, the splines follow the original function very closely across the entire intervals. And to make it clear, let's compare Lagrange Lagrange interpolation, clamp, and natural cubic splines. All three methods pass through the same data points, but the behavior between the nodes is different. The spline generally follows the function more smoothly because this is as a piecewise function, while the Lagrange polynomial function or Lagrange interpolation, because this is as a global interpolation, can show larger deviations from the original functions. The clamp splines, but if we compare the clamp and the naturals, the clamp spline often give a better match near to the endpoint because it uses the known slope informations. This is about this is the comparison between the global and the local interpolation. Let's summarize some key points about the end conditions. First, we are not limited to only natural or clamp conditions. We can also mix them depending on the problems. Second, we can impose other type of boundary conditions, such as periodic conditions, which are useful for closed curvature. It can, in this case, the function and its derivative match at the endpoint. Third, spline can also be used to estimate values outside the data range, but since they are designed for interpolation, the accuracy may decrease when we're doing the extrapolating. The key point in that we always need to specify two boundary conditions to uniquely determine the splines. Okay. This graph shows a comparison of the natural mix, mix and cram cubic splines with the same data points. If you look at the figure, the natural cubic spline deviates more between the data points compared to the other method. So the error is larger. This happens because the natural splines assume zero curvature at the endpoints, which may not reflect the true behavior of the function. On the other hand, the cram and mix spline use additional boundary conditions, boundary informations, so they match the original function more closely. And if we compare the Lagrange natural cubic splines, okay, with the wrong functions, okay, we get these graphs, okay. As you can see, the Lagrange interpolation pass through all the data points. It exhibits large oscillation, especially near the endpoint, because high degree polynomials can become unstable. On the other hand, the black curve that is represent the natural cubic splines, okay, this is as a piecewise local interpolation. It produces smoother and more stable approximations and follows the true function more closely. This example demonstrates that cubic spline typically offer better accuracy and stability than using one high degree polynomial over the entire intervals. This is the end of this lecture. Thanks for watching.